Hi, everyone. Welcome to the third session of the second day of Latin Crypt. This is also the last session of today. And this is the second session on cryptanalysis and side channels. We have 3 talks in this session for you. The first talk is going to be about autocorrelation of vectorial Boolean functions. It's work by Canteaut, Lukas Kölsch, Chao, Chunlei, Kangquan, Longjiang, and Friedrich Wiemer. And Chunlei will give the talk.
Hello, everyone. My name is Chunlei from University of Bergen in Norway. It's a great pleasure for me to present our recent work, Autocorrelation of Vectorial Boolean Functions at the Latin Crypt 2021. I would like to take this opportunity to thank the organizers and the program committee for their contributions to the workshop. This is a joint work with Canteaut from INRIA Paris in France, Lukas Kölsch from University of South Florida, USA, Chao Kangquan, Longjiang from National University of Defense Technology, China, and Friedrich Wiemer from Ruhr University, Bochum, the Crypto Solutions Group in Germany. In this talk, I will start with general research background on vectorial Boolean functions in block ciphers. And then I will introduce some cryptographic criteria on Boolean functions and discuss their relations. After that, I will focus on the autocorrelation properties of vectorial Boolean functions. Finally, I will summarize our contribution in this work. As we know, symmetric ciphers can be expressed mathematically in this way. The cipher takes n-bit key and n-bit plaintext. After some operations, it outputs the ciphertext, which has n-bit. The block cipher can be seen as a set of randomly generated permutations indexed by a given key. And this typically, the block cipher is a sequence of completed permutations in this way. So here, the given key is used to generate the round keys for each round. Then these functions completed. Finally, it outputs the ciphertext. In these round functions have the same structure, and in each round key, each round, the only nonlinear component is the substitution box, also known as S-box for short. The design of S-boxes play a very important role in the security of block ciphers. So let's look at the properties of S-boxes when it is used in cryptographic applications. Mathematically, we can express an S-box with n-bit in, n-bit out as a mapping, like from f2 to the n to f2 to n. Here, f2 is a set of 0 and 1. This mapping is also known as a vectorial Boolean function in the community. There have been many criteria proposed for S-boxes in the from the cryptography perspective, and these criteria is the major focus of our talk. Let's start with linear approximation table, which is related to the nonlinearity of the function. It is defined from the Ghosh transform of the function f. Like here, it's also the discrete Fourier transform of -1 to the power v interpreted by f of x. So the LAT of f basically consists of all the possible Ghosh transforms for different u's and v's. And the linearity of f is defined as the maximum absolute value of these Ghosh transforms, and it is known to be lower bounded by 2 to the power n over 2. Accordingly, the nonlinearity of f is defined as 2 to the power n minus 1 minus the half of the linearity of the function f. The nonlinearity of the function f is used to assess a strength of f against the well-known linear cryptanalysis. And f with high nonlinearity is desired in cryptographic applications. Another important criteria is the differential uniformity, which is defined from differential description table, DDT for short. Given a function f, this function, the derivative function at u, and based on this one, a given v, then the number of solutions to this equation is known as the differential property of the function f. Then if we arrange all these values in a table, it is known as the DDT of the function f. And we take the maximum value of all these values for all non-zero u and v, then it is easily shown, it is easily seen that these differential property du, df at uv has at least 2 solutions, like here, because this equation has solutions in pairs. If x0 is the solution of this equation, s0 plus u is also a solution. And when a function achieves this equality, it is known as almost a perfect nonlinear function, APN functions for short. The differential uniformity of a function f is used to assess the strength of the function against the differential cryptanalysis. And it is known that in block ciphers, we would like to have a function with as low differential uniformity as possible for security. Differential cryptanalysis is a very powerful attack against the block ciphers. There have been many variants proposed in the literature. One of them is a boomerang attack. It was proposed in 1990s, and in 2018, some researchers extended the idea and further improved the performance of boomerang attack. Accordingly, there's a new cryptographic criterion of S boxes. It is defined in this way. So here, the inverse of the f is also involved in this definition. And it is similar to the definition of the differential property of f, but it's more general. And the boomerang connective table is the table consisting of all the possible values of the BCT of f at all the UVs. And the boomerang uniformity of f is defined as the maximum value when u and v range through f to the power n. And it is shown that the BCT of f at uv is always equal to or larger than DDT of f at uv, which is lower bounded by 2. And this boomerang uniformity can achieve this minimum value 2 if and only if the function f is an APM function. This solution was later extended to long bijective functions as well. And the function can be defined over fq to the n to fq to the m. In general, this parameter is used to assess the function f against the new boomerang attack. And we prefer to have low boomerang uniformity of the function f in block ciphers. Motivated by the sandwich extension for boomerang attacks and illusion of BCT and boomerang uniformity of vectorial Boolean functions, recently some researchers proposed a new notion, differential linear connective table, to analyze the transition between the differential and the linear parts of a vectorial Boolean function. It is defined in this way. It turned out that this notion is not really new. It actually is a variant of the autocorrelation of a vectorial Boolean function, which was defined in 2000. And we have shown that the autocorrelation of f at uv is actually the double of DLCT of f at u and v. And we can arrange the autocorrelation function at u and v in a table for all u and v's. And we have enough information about the DLCT property of the function. We define the autocorrelation or absolute indicator of the function as the maximum absolute value of autocorrelation f at uv as u and v runs through all non-zero elements in codomain and domain. This parameter of vectorial Boolean function is designed to be low for cryptographic applications. Now we move on to the third part, autocorrelation properties of vectorial Boolean functions. So first, we'd like to know the relations between the Lowen cryptographic criteria, LAT, DDT, BCT, we have introduced before, and ACT of vectorial Boolean functions. So first, the autocorrelation of f at u and v can be expressed in terms of the watch transform in this way. Now, with this relation, we can obtain that the sum of autocorrelation of f and u and v as u runs through f to the n equals the watch transform of f at u0 and v squared. We also obtained some relation between DDT and ACT. Similarly, the autocorrelation of f can be expressed in terms of DDT as the sum of this DDT with omega in the code ranging through the codomain. And with this relation, we obtain some result on the sum of autocorrelation of f, like these two. We also obtained some relation between BCT and ACT. They are given in this form. For autocorrelation function property of vectorial Boolean functions, we would like to know the lower bound of this parameter. First, we obtain a result about the sum of autocorrelation of f as uv runs through f to the m. They are lower bounded by 2 to the n plus 1. The equality here holds for all non-zero u if and only if f is an APM function, which has the best possible property against the differential cryptanalysis and the boomerang cryptanalysis. And the autocorrelation indicator of a function f is lower bounded by this term. And when m equals n, this term can be simplified as 2 to the power n over 2 together with another bound. We also obtained some divisibility about the values of autocorrelation for vectorial Boolean functions in terms of their algebraic degrees. Here is the result. The value of autocorrelation of f at u and v is divisible by 2 to the power this power. Here, d is the upper bound of the vectorial Boolean function, the upper bound of the algebraic degree of the vectorial Boolean function. When m equals n and f is a permutation, then this term is reduced to 8. When a vectorial Boolean function has a specific algebraic degree 3, then we can obtain the values of autocorrelation function of u and v in more speculative form, like this. But here, the exponent is given in terms of u and v in this definition. And in the study of cryptographic Boolean functions, there are 3 Lewin equivalents between 2 functions. They are affine equivalence, EA equivalence, and CCD equivalence. It is shown that affine equivalence is a subset of EA equivalence, which is a subcase of CCD equivalence. And under the most general CCD equivalence, we know that the nonlinearity of a vectorial Boolean function and the differential uniformity of a vectorial Boolean function are invariants. So what about the autocorrelation property? Well, under EA equivalence, the extended autocorrelation spectrum defined like this are the same. If under affine equivalent, then the autocorrelation spectrum without this absolute value, they are the same. So this shows that the AC spectrum is an invariant on the affine equivalence, and extended AC spectrum is an equivalence on the EA equivalence. And there's a low invariance property of AC under the most general CCZ equivalence. We also considered the AC properties of certain vectorial Boolean functions of more cryptographic interest, like the inverse function. Here we obtained the AC spectrum of the inverse function used in AES, like this. And here the k, the parameter k of v, is the Klosterman sum. The autocorrelation indicator of f is can be also given if n is even, like this, and if n is odd, we can express the autocorrelation indicator in terms of the linearity of the function, like in these 3 values. Finally, we considered the autocorrelation property of some power functions, which have good cryptographic properties regarding nonlinearity and differential uniformity. So we have considered 6 families of power functions. We give either the specific values of the autocorrelation indicator of the function, or the possible values, or some upper bounds of the autocorrelation function. To summarize, in this paper, we clarify the relation between the DLCT or AC property and the Lewin criteria LAT, DDT, BCT of a vectorial Boolean function. We investigate the bounds, especially lower bounds, on the absolute indicator of vectorial Boolean functions. We discussed the invariance property of AC on the affine EA and EA CCD equivalence. Finally, we studied a number of cryptographically strong Paul functions and other functions in terms of their AC properties. That's all. Thanks for your attention. If you have any question, please feel free to send your question to this address.
Okay, thanks, Chunlei, for the talk. We are going to move to the second talk of this session, which is on automatic search for bit-based division property. Joint work between Shibam, Ghosh, and Dunkelman. And Shibam is going to give the talk.
Hello and welcome everyone. I am Shibam Ghosh and I am going to discuss on automatic search for bit-based division property. This is my joint work with Professor Dunkelman at University of Haifa. Here is the outline of our talk. We will first discuss some background on division property and our contribution. The division property was introduced as a generalization of integral property by Todo in Eurocrypt 2015. A full-round attack on MISTY-1 was introduced by Todo in Crypto 2015 using division property. The bit-based division property, which can capture information from bit level also, was introduced by Todo and Mori on FSE 2016. The automatic search for bit-based division property was introduced by Jiang and others. And this was mixed integer linear programming based tool. SAT-SMT modeling and CP-based modeling was introduced by Sun et al. On 2017. Here's our contribution. We propose a compact conjective normal form using Quine-Mikulski algorithm for the SAT-SMT and CP-based approach. We propose a concrete algorithm for finding lower data distinguisher. As a result, we find more efficient distinguisher on NOT and ASCON. And we discuss some result on extended division property. As a result, we prove there is no integral distinguisher on 18 down NOT 256 and 384. Here is our improved result. We find improved result for NOT 256 and 384 in 17 round and 18 round, for NOT 512 in 19 round, and for ASCON in 5 round. Here is some notation we will use throughout our talk. So the first one is for all vectors k and k dash, we define k is a successor of k dash if ki greater or equal to k dash for all coordinates I. The bit product function corresponding to a vector u is defined by pi ux is the product of xi to the power ui. That means this is a monomial where ui used as a selector from the x coordinates. Algebraic normal form is the XOR sum over all possible vector from f2 to the power n of the bit product function. Here to vector we introduce in and out input property and output property, where in is the vector which is all coordinates are 1 except for the position I1 to IP, and out is the vector where all coordinates are 0 except for the position J1 to JP. Similarly, as a vector, we can define this notation for matrix also. So if we have a matrix, then the subscript are two-dimensional coordinate, where all coordinates 1 for in except for the position k1 l1 to kp lp, and for out all coordinates are 0 except for the position u1 v1 to up vp. A multiset X is said to have the bit-based division property dkn for some n-dimensional vectors k, set of n-dimensional vectors k, if it fulfills the following condition. We take XOR sum of pi ux, that means bit product function corresponding to u, over the set capital X, and if there is k greater belongs to k such that u is a successor of k, then this XOR sum is unknown, otherwise this XOR sum is 0. So here's the definition of balanced position. Let Y be a multiset of vectors, n-dimensional vectors. A bit position I is called a balanced bit position if the corresponding coordinate over XOR sum over the set Y is 0. Then we discuss how to search for piece-based division property and how to model and automatic tools on the search. So here we introduce the division trail. Let us consider a primitive f with round function f0 to fr. We can have such a chain of division property where the input is singleton set k0 and then k1, k2, and so on. The condition is for any vector ki belongs to capital Ki, there must exist a vector ki minus 1 such that ki minus 1 can propagate to ki by the division property propagation rule. So we discuss the definition of division trail. Now we discuss how division property can be propagated through different functions present in the round function. So first of all, the propagation through Xbox layer. Propagation through Xbox layer was proposed by Zhang et al. This is an exhaustive search for each possible input. So we consider an input vector A, and we compute the following set of monomials f(a)x. And for any u, if pi ux contains a monomial from f(a)x, then u is in the output set corresponding to A, that is Ka. Propagation through linear layers. So bit permutation are easy to model. For matrix multiplication, we need rank method proposed by Zhang et al. And that is AU is a valid division trail through a matrix if the corresponding m' matrix has rank weight A, where m'(ij) is mij product with aj, a product with ui. Here we discuss how to set input property and output property in a search. For the input property, we will use embedded property. For two vectors k0, which is successor of k1, if the output multiset under k0 does not have any balance bit, then the output multiset under k1 also has no balance bit. And corresponding to this property, we take the input property with n size n minus 1. That is INI for all possible I. For the output property, this proposition is that if X is a multiset with bit-based division property dk1n, then X does not have any balance bit if and only if K contains all the vectors of weight 1. So for the output set, we consider the output property as outj. That means all possible weight 1 vectors. So this is how we get input property and output property. We set the input property and output property in the CNF or a SAT model. Then we'll check for satisfiability. So here is an example how to model such a CNF formula. This is an example on Canteaut S-box, and this is the division property, bit-based division property propagation table on Canteaut S-box using Zhang et al.'s algorithm. So the left-hand side is the input property and right-hand side is the output property set. Corresponding to each element in the left-hand side and corresponding elements from output set, we can consider a vector of size 8. So each of these 8-bit vector is a valid division trail, and corresponding to each input and output, we can construct such vectors. Then, depending on this vector, we define this function fs, which is defined on A concatenate with B, is 1 if AB is a valid trail and 0 if AB is not a valid trail. And we use Quine-Mikulski algorithm to find minimum size CNF of fs. So what's the data complexity of such a distinguisher? So if the input property is k, then this distinguisher uses a set of plaintext vector x such that ith bit is constant, ki is equal to 0, and other bit takes all possible values. So data complexity of this distinguisher is 2 to the power weight k, and consequently, if the input property is I and I, then data complexity is 2 to the power n minus 1. So here we discuss how to reduce this data complexity. So here we define 3 sets. The first one is S, is the set of all index I such that there exists J with I and I to out J is a valid division trail. Out I is the set of all index J such that I and I to out J is a valid division trail. And IN2 is the all possible pair I0, I1 from S such that out I0 intersection out I1 is not equal to phi. That means they have a non-empty intersection. Then from this IN2, we search with input property IN I0, I1 for each IN I0, I0, I1 belongs to IN2. And if we succeed to find a balance bit, we can reduce the data complexity by 1. In this case, search is easy. We search only over out I0 intersection with out I1. We can generalize this idea to INM easily. And here is the proposition: if M0 and M1 two non-zero integer with M0 less than M1, and if there is no balance bit from INM0, then there is no balance bit from INM1. So we'll start our search from lowest possible value, that is 2. Here we discuss some experimental result on NOT. NOT is the permutation that is the main primitive used in NIST LWC submission NOT family. Each state is 4 cross B matrix where B is equal to 64, 96, and 128, corresponding to the block size 256, 384, and 512. In each state, we use an SP network that consists of 3 operations: add round constant, subcolumn, and cipher. As we know, the round constant does not affect conventional bit-based division property. So we take variables for subcolumn and cipher only. So here is the variables in SAT or CT model. This is the chain of propagation of variable. We take an input property at A0. Then after S box, this variable becomes A1. Then after rotation, this is B1, and so on. Now we see these red color variables B1, B2, and so on. These are the rotation of previous A1, A2, and so on. So we do not need to add a new variable for this B1. We just rotate the vector A1 and to the input to the next S box. So here is the first result. If we set the input property as IN30, then we get such results where number of balance bit for not 256 is 89, not 384 is 140, and not 512 is 269. The right hand 4 columns, which are SAT, CNF, CP, CSP, CP, CNF, gives an important information. So this CP and CP, CNF are differ in the case that CP is implemented with the table-based model, where CP, CNF implemented with our compact CNF model. And we can see we can improve the efficiency hugely by this CP, CNF formula. Same for SAT, CNF. Here is the second result. Earlier we defined the set S. Here the result is S contains all 4 cross B coordinates. That means from any INKL we have a valid division trail. So now we discuss how to reduce this data complexity. So the idea is try different combination from S as we discussed previously, but S is huge. So we use a subset of S, that is S dash, which is the first column. We try different combination from S dash and try to improve the data complexity. So here is the result on NOT 256, 384, and 512. For 17 down NOT 256 and 384, we improve the data complexity to 2 to the power 254 and 2 to the power 380, and for NOT 12 to 2 to the power 508. So here we discuss what's the time requirement for this reduction. So as we saw earlier that this search is easy as we search only in the intersection of outsets. So this time requirements is negligible. Here is other experimental result in rectangle, present, and gift, where we proved previously proposed result. Now we discuss on extended division property. This was introduced by Lambin, Derbez, and Fogg in 2020. The idea is division property are not invariant. So for a given R-round primitive ER, we can consider L-out composition ER composition LIN instead of ER, where L-out and LIN are two linear map. This way, we may get some distinguisher on L-out composition ER composition LIN, which is not possible on ER. We focus only on linear mapping, which are block diagonals, each block corresponding to an M-bit S box in the S box layer. But the problem is this search space is huge. So here we reduce the search space for L-out. the idea is proposed by Derbez and Fo that finding proper linear combination of the output bits instead of linear map is enough. And this reduces the search space to 2 to the power m minus 1. So if an S box map from S vector to Y vector, then this 2 to the power m minus 1 linear combinations are P1, P2, and so on, where each PC is the dot product with C0 to Cm minus 1 with Y0 to Ym minus 1. And this PC is C is the integer binary representation of this vector C0 to Cm minus 1. And this reduce the search space 2 to the power m minus 1, but still, do we need to check all these 2 to the power m minus 1 polynomials or not? So here we discuss how to reduce this further. So here is what is we need to check. So if f is a Boolean polynomial, then f is called even polynomial over a multiset x. Each term, XOR sum of each term over the multiset x is 0. And let us consider two Boolean polynomials p and q. We say q is dependent on p if any monomial or term in p divides at least one monomial or term in q. And the proposition is, if we have two combination of polynomials p and q with q dependent on p, and we can find that p is not even, then q is not even. According to the dependency relation defined above and the proposition defined above, we form a few cluster of polynomials. Then checking a single polynomial is even or not, we can decide about all other polynomial in the cluster. So here is the implementation of that idea. We consider a dependency graph G. Each vertex Vp corresponding to a polynomial P, and there is a directed edge from Vp to Pq if Q is dependent on P. Now we choose a starting vectors and try to construct a path. All the vertices Vq that fall in the path from Vp must satisfy the relation that Q dependent on P. So checking the starting vector, we can decide about all other polynomials. So here is the result on not S box. We get different length path from different starting point, and the red points are the starting vertex. So this first row started from VP4. So how to decide final trails for the K not S box? So one of the maximum length paths start from VP4. First, we remove all the vertices that are reachable from VP4, and we form a cluster with those vertices. The next path start with VP8, and as the VP8 was not removed, so we start a search from VP8 and construct a cluster with remaining vectors and so on. In the other case, if VP8 was removed previously, then we go to the next starting point and so on. So this is how we find the final trails for the not S box. So first trail is starting from 4, then 8 and 12. So we have to consider these three polynomials, which is y2, y3, and y3 XOR y2. And we can observe that x0, x1, and x1, x2 are present in each polynomial. So if these monomials are not even, then we cannot find any useful property. So we check for this monomial. To check for this monomial, we prepare the following output set, the following output property, and the result on not 256 and not 384, that x0, x1, and x1, x2 are not even for any Xbox output after 18 down. So we can conclude that we cannot extend the integral distinguisher to 18 down by this method. Also, one important thing to notice that this linear combinations also cover all the input on all the identity vector also. So we cannot even extend the 18 down distinguisher for not 256 and not 384 using conventional division property. And we prove this result more efficiently than usual method, because corresponding to each S box, we are checking for 2 output property instead of 4 output property. Here we conclude our talk. We discuss a compact way of modeling SAT-SMT and CP-based model to search bitbased division property. As a result, we found lower data distinguisher or not and ASCON. Extended division property, we discuss a precise way to find minimal number of linear combinations. And as a result, we discuss that 18-down integral distinguisher using conventional division property on 18-down not 256 and 384. There is no such distinguisher. Thank you for your attention.
Thanks, Shibam, for the talk. We'll have the questions at the end of the session after the next talk, which is on highly secure leakage-resilient tweakable block cipher-based AE, which is by Ike Lest, and Ike will present the talk as well, actually.
Welcome. This talk is about TDD2, a highly secure, leakage-resilient authenticated encryption scheme based on a tweakable block cipher. Authenticated encryption is an important cryptographic primitive. It protects both the authenticity or integrity of data as well as its confidentiality. Usually, it does so with the help of a unique nonce per encryption, a number used once. From early generic composition, it has evolved to a primitive of its own. Many dedicated standards have evolved, such as GCM, OCB, and others. Moreover, many dedicated schemes have evolved over the past years to fulfill certain properties particularly well. On one hand, there is, for example, the wish for high efficiency, be it in terms of low area or high throughput. On the other hand, there is, of course, the aim for high security. Moreover, robustness properties have evolved as desirable for OAE. At the beginning, robustness meant to establish security if nonce is repeated. It was later augmented to such cases as distinguishable decryption failures, or to the case when information about invalid plaintexts were given to the outside world, to such strong forms as robust authenticated or subtle authenticated encryption. In addition, subtle notions evolved such as nonce misuse resilience. It means that a scheme cannot provide any security while nonces repeat, but it can, again, preserve security when nonces start to be unique again. The most difficult and the broadest form of robustness is resilience against leakage of arbitrary internal values. Leakage resilience has been established as a desirable property long ago. Thus, many works have addressed leakage schemes since the seminal early works. Though modeling it has not been and is still far from being trivial at all. Therefore, several concurrent approaches have remained whose conceptual definitions differ. Three main definitions or schools of thought can be identified. The first one is the school of only computation leaks, or OCL, given by the seminal work by Micali and Racine. It defined that only calls to functions may leak internals, which is handy to prevent caring about storage leakage. OCL bounds the amount of leakage per primitive call to some, say, lambda bits. The approach found wide attention. Though, in practice, leakage is often noisy and can be measured potentially many times. Simulatability is a second approach. Here, the ideal word tries to efficiently simulate the leakage of the real construction. Though, early simulators were broken soon after their proposal. While the setting remains interesting, it is an open problem to come up with efficient simulators. A third school, around François-Xavier Standard, has introduced a third approach that allows unbounded leakage. To prevent simple attacks that are mostly of theoretical nature, it needs that leakage is not efficiently invertible and that leakage functions cannot call the used primitives as oracles. The approach also captures multiple randomized leakage results. As is OCL, this unbounded leakage model is also widespread, though it is mainly put forward by the group around Standard et al. According to its authors, the model is a little more complicated to handle and to achieve, but it reflects the practice better. Therefore, we consider it also in this talk. Leakage-resilient authenticated encryption schemes became interesting study objects during the past decade. For the OCL line of research, the framework of notions by Babel et al. Ignited a series of works. Besides their framework, they also showed that a variant of encrypted MAC can be secure. Thereupon, schemes such as ISAP or FGHF' were proposed and analyzed. Since they were based on permutations, also sponge and duplex and their leakage resilience has been studied. In the unbounded leakage setting, a similar framework of notions arose iteratively. Those notions were summarized recently by Gu et al. At LatinCrypt 20. This direction also saw many schemes that have been proposed over the past years. Many of those were based on block ciphers, with the motivation that such schemes can have a smaller state and could be protected at lower costs than with permutations. One of these schemes is, for example, TDT, which shares some similarities to ISAP and FGHF'. From a high-level view, those are structurally very similar. First, they derive an initial value from a nonce and a strongly protected key derivation function. The initial value is then used as a seed for a fully leaking keystream generator, whose keystream is added to the message. Thereupon, the ciphertext, associated data, and nonce are hashed, again fully publicly, and their final hash is processed by a more secure function to derive a tag. Two passes and the encrypted MAC order have been shown as necessary and sufficient for security under leakage. A single pass encryption could not provide CCA security, and should the message be authenticated before encryption, this might leak the would-be plaintext. The structure of this has been called by De Gabriel et al. FGHF', which motivated them for the name of their scheme. The difference between these three schemes lies in the details. Our focus in this work shall be on TDT. It uses a tweakable block cipher in two implementations. For IV derivation and for tag generation, a strongly protected implementation is used. Moreover, it decrypts the tag for verifying the integrity. This decryption prevents that a would-be tag for an unauthenticated ciphertext could leak. Thus, the message is not even decrypted if the tag is invalid, and thus it cannot leak. TDT provides high security in the black box model and for integrity under leakage. However, its authors could only give a tight birthday bound for privacy under leakage. The scheme is interesting for its efficiency and for its leveled approach. This means that only very few calls to a primitive need strong protection, namely the first for IV generation and the first for tag generation. However, we found room for three slight improvements that we addressed in our construction called EDT2 in this work. In total, we considered four aspects. In general, we employed a Tweaky-based tweakable block cipher, where Tweaky is a framework by Perrin et al. That says that key and tweaks should be processed equally by a so-called Tweaky schedule. We propose to extend the cipher using one with 3 n-bit tweak and key, compared to one with 2 n-bit tweaky for TETT, considering the hash function, moving the nonce, and strengthening the encryption scheme that we will detail a little in the following. Firstly, we considered more efficient hashing. TETT used Hirosi's compression function together with Merkle's-Domgaard strengthening. We propose to replace the strengthening by Hirosi's so-called MDPH construction that had also been suggested in parallel for the AE schemes Romulus and AEDLR. Given a primitive with 3 n-bit tweak and key, the hash function can use 2 n-bit message blocks now instead of n-bit message blocks. Thus, the larger tweak spares half of the primitive calls. Moreover, Naito recently showed an improved security analysis for Hirosi's MDPH construction. This spares the finalization and saves 2 tweakable block cipher calls. Secondly, TEDT, as ISAP and FGHF' processed nonce, associated data, and the ciphertext in the hash function. There, TDT splits the 2 n-bit hash into 2 n-bit parts. One n-bit part is used as the input to the finalization function, the other n-bit part is used as tweak input. We propose to move the nonce from the hash function and use it directly as a part of the tweak in the tag generation. This saves on average one primitive call in the hash function, depending on the length of padded message and associated data. Thirdly, TEDT uses a variant of rekeying counter mode for encryption. This wait 1/2 scheme was almost n-bit secure in the black box setting. Under leakage, it could provide only n-half bits of security from a hybrid proof argument. Given a larger tweak for our primitive, we propose to use a 2 n-bit secret tweak key per iteration that is used for 2 n-bit message blocks and their encryption. This preserves the rate of 1/2 and close to n-bit security in the black box setting. However, it also preserves close to n-bit security under leakage, since we now have a larger tweak key and therefore the same hybrid argument exceeds the birthday bound now. We used a framework by Gu et al. That considered unbounded leakage. We adapted it to a common single-user setting where multiple challenge queries are allowed. As a slight detail, we changed the left and right style consistently to the more common reload random notion. However, please note that this means only that the oracle samples a random message in the ideal setting, but still processes this message also with the real construction. The cause is simple: it would be hard to simulate the leakage from some ideal construction. The framework explicitly separated integrity and confidentiality. We used versions of their notions for ciphertext integrity and for chosen ciphertext confidentiality. Integrity can be fulfilled even if nonces repeat, which is denoted by the capital M for misuse resistance. The 2 at the end means that 2 leakage oracles for n in decryptions are available to the adversary. For confidentiality in the chosen ciphertext setting, nonces must not repeat for challenge queries, but can also repeat for non-challenge queries. This is indicated by the lowercase m. However, for confidentiality, we needed to adopt 2 necessary auxiliary notions. One is indistinguishability of XORs. That means that XORs may leak through the scheme. And second, the unpredictability of an iteration of the encryption. The latter may need few more words on it. The notion of unpredictability under leakage captures that of a tweak key during the encryption. Here, the adversary sees p leakages of n and decryptions of one iteration of the rekeying counter mode. The inputs can be chosen by the adversary. However, the challenger samples secret inputs to the previous iteration and gives the output of 2 such iterations in addition to leakages to the adversary. We adopt this notion from the TTT setting to the larger encryption scheme and its iteration used in TDT2. In the following, we give a brief sketch of our analysis. We can follow the footsteps of the proofs by TDT, but need to adapt a few stages where our construction differs. The integrity analysis consists of 3 steps. First, we replace the strongly protected calls to the tweakable block cipher used for IV derivation and for tag generation by ideal tweakable leak-free permutations. Second, we bound the probability of partial collisions and multi-collisions in the hash function. We bound the probability then also of partial collisions and multi-collisions in the tweak input for the tag generation function, and we bound the probability of forgeries without such collisions. If none of this happens, one cannot distinguish the world. As a result, we arrive at the following bound, which means that we take into account the sum of all the collision, multi-collision and partial collision events, replacing the IV derivation and the tag generation function by ideal functions, and we arrive at a term that is equivalent to n-log n bit integrity security for our scheme. Moreover, some words on the proof sketch for confidentiality. Here, the analysis is twofold. First, we can consider fresh decryptions. From the structure of our construction, we can hereby observe the following. If a ciphertext has not been produced from a previous encryption, it must be a valid forgery to get any leakage from the decryption property that is not simply because of the public hash function. If a fresh tuple of nonce, associated data, tag, and ciphertext is decrypted, it must be a valid forgery. Then we can upper bound the probability of that by that of our previous proof and can consider hereafter that no valid forgery occurred. In this case, from decryptions, only the valid hash leakage will occur. If the adversary cannot forge, security reduces to the privacy against chosen plaintext attacks. Though, note that the adversary can still query valid decryptions and obtain also decryption leakage. We can upper bound this by the probability of internal tweaky collisions and have to address two auxiliary terms as said before. These capture that each iteration of the encryption scheme may leak if the real or random message block was encrypted, and it may occur that each XOR operation may leak. We cannot bound the terms for the XOR leakage in theory as the original TDT. As then, we have to leave this term for lab settings when the scheme is instantiated with concrete primitives. Moreover, the unpredictability is derived from the equivalent bound of TDT, only that the tweaky now consists of 2n bits and we arrive at a larger bound. For the remaining bad events, we upper bound the probability of tweaky collisions between blocks in the encryption scheme and between that and primitive queries and calls to other parts of the scheme. To sum up, we obtain the following bound under leakage that is close to n-bit security for the CPA bound. The integrity term is contained and means that security is bounded by n minus log n bits. Note that CCA provides at most nonce misuse resilience, but no nonce misuse resistance. In the plot, the lines of the integrity security of TDT and our construction match. Though the unpredictability of an iteration of the encryption scheme captured in the unpredictable of 4 blocks produces or has produced the worst security line for the original TDT. For our construction, this line has moved close to the other bounds. In sum, our goals for improving TDT were threefold. For all of these points, we profit from a tweakable block cipher with a longer tweaky. First, we aimed at more efficient hashing. Here we could benefit from the high rate of the larger tweak. Moreover, we can use Nito's recent bound of MTPH to spare the finalization. We do not claim this point is novel, as parallel to our work, we found it also adopted by the AE schemes AET and Romulus. However, those are by far less robust under leakage in terms of security than TDT. Second, we removed the nonce from the hash function inputs and used it in the tag generation function. Thus, we spare one primitive call on average in the hash function. Third, we extended the encryption scheme for higher security under leakage. TDT used wiki in counter mode with 2 primitive calls per iteration that we extended to 4 calls per iteration to derive a 2-bit tweaky. Thus, the hybrid argument for the unpredictability of an iteration is no longer of birthday type in terms of n, the state size of the primitive, which was the bottleneck of the privacy bound. TDT is already a very strong authenticated encryption scheme under leakage. Our improvements were natural and rendered TDT as its second iteration more efficient and more secure. We identify several directions of potential further aspects of future work. Parallel to our work, the group by Perrin proposed the development of tweakable block ciphers with even larger tweaky. Such constructions could be used for even considerably more efficient hashing. Moreover, one can generalize the encryption scheme for even more blocks to increase the rate further. However, Note that more blocks would need a more detailed study of the leakage and the implications to an adversary. Finally, our analysis considered the security in the single user setting. This is the most common setting, though an interesting future work would be to consider multiple users again. With this, I would like to close this talk and thank you very much for your attention.
Okay, thank you, Ike, for the talk. Now the floor, or rather the cables, are open for questions. So if there are any questions from the audience, we can have them. To chat, so you can ask questions from any speaker that you like in any order. So it's more of a panel discussion. So maybe I'll ask one question from Ike to start with. So my question today is the relation between your model and indifferentiability. I looked at authenticated encryption schemes under an indifferentiability framework, and I was wondering how this relates. And if your security model, for example, is a single stage or multi-stage. And also a follow-up question is, you mentioned the simulation-based model in one of your slides, and that somehow this still remains open, and how that also relates to the indifferentiability model.
I must admit, the second question is hard. I don't really know the detail how it relates to the indifferentiability model, the simulatability model. This is still open, and as far as I know, the group by Standard et al. Still tries to get this done because it's still the most interesting direction. For your first direction, I know that Leakage-resilient is a multi-stage game, but it's one that can be modeled in some not so hard multi-stage setting. I don't know how the model exactly relates to this, but indifferentiability is definitely a very interesting approach still for capturing leakage resilience. But it's not covered in this work, definitely. But still, it's open to do indifferentiability proofs. This would, as far as I know, still be a highly interesting direction for many more schemes.
Okay, so you're saying the game is multi-stage. The leakage game that you're looking at.
This game, what I did is just standard model, but I know that Leakage Resilience is an instance of a multi-stage game, but I don't remember exactly what was the notion. Was it your paper actually?
Yes,
Either it may be your paper that said that this is possible, this Leakage Resilience is possible to cover with indifferentiability.
Yeah, I was just wondering.
One paper that cited yours.
I was just trying to look at your paper to see what the model is, and what sort of, if it is 2-stage or 3-stage, so or multi-stage. So
no, I didn't use anything about indifferentiability, but I know that indifferentiability is still a highly interesting approach for that, but this was not covered in that work.
So what is left open in this area of leakage resilience for authenticated encryption? What are some of the driving questions?
I would say that a lot of things that I'm also not the best one to be addressed by that, because there's the group by Dobraunik and Manning who did a lot of works in the OCL area and are highly convinced to have a very good model, and I would not disagree with that. On the other hand, there's just this other group of Standard et al. Who rather uses the unbounded leakage setting. All of this has their relevance, but you already said it. I would say that indifferentiability is still a highly interesting approach, and there is still much to look into how it could be used to model or to bring up even stronger proofs for leakage-resilient schemes.
Okay. Thanks very much. Any other questions meanwhile? Or if not, I'll ask Shibam a very general questions. I am not working in this area, so my question might come across as quite uneducated. So my question is, once these attacks are improved, for example, the data complexity of the attacks are improved, as you said in your talk, what is the effect on the standardization process? Do the proposer go and change the security parameters or the number of rounds for their schemes? How do they respond when?
Okay, so when we publish those paper, this paper, it was already announced the finalist for the NIST competition, and not was out of the finalist. So yeah,
Was not.
No, was not in the finalist list. So yeah.
But if it were, say, if is your paper one of the reasons that it was not, or?
That I am not aware of, but I think the most important thing of our paper is number of balanced bit, which was in the original proposal. It was only one balanced bit they found after several days of experiment, but as we have seen, we have found many balanced bit, almost nearly 100. So it is a real vulnerability in my sense. Yeah.
Okay, and does it extend to any of the finalists or NIST lightweight competition? Does your methods? I'm sorry.
Sorry.
Does it extend to any of the finalists? Your attacks?
Yeah, ASCON. ASCON is yeah. ASCON is on the finalist.
Okay. Have they responded to your attacks?
No. I mean, there is. I mean, this sort of algebraic properties. I mean, once they propose the scheme, there is very less chance to modify those to recover those algebraic properties. I mean, these algebraic attacks. But for ASCON, this is only 5 rounds attack, and it has 7 rounds. I mean, the ASCON permutation has 7 rounds, so it's not a problem till now.
Okay, thanks. Are there any other questions for any of the speakers?
No.
So if not, then this is the last session of today. And I think there are some events coming afterwards. And I think Valerie has some announcements about that. So I will pass over to Valerie.
Thank you, Pooya. Thank you to all. Yes, so we finished the academic part of today, but we will wait for you in 1 hour and 20 minutes at 2 p.m. from Colombian time to do a virtual tour to a traditional Colombian coffee farm. So I hope you will join us and enjoy it. And so if you go to the main page to the left, there is a menu. You can click there to the visit to the traditional Colombian coffee farm, or you can go to the house of a Colombian house and click in the picture of the coffee farm. And tomorrow at 6 a.m. we wait for you because we will see the awakening in Colombia. So the waking up of the Colombian region. So there is some hidden cameras and there are some food for the birds. And usually they come around 90 different species of birds. So you can listen to them and hear what is it. In Europe or Asia, I think it's a little bit later. For us, it's really, really early. But I think it's a nice experience. I hope you enjoy it. So we wait for you at 2 p.m. tomorrow at 6 a.m. And we will resume tomorrow at 7 the Latin encrypt sessions. So thank you a lot.
Yep,
Bye.
Thanks. Bye. Yep.